Good afternoon, ladies and gentlemen. I'm not able to speak in Castellano, so I will speak in English. I apologize because my English is not so good. It's my third language. I'm here exactly the site manager, and the job at the Polytechnical School in Lausanne take me perhaps 5% of my time, and 95% of my time is to be the general site manager of this job. We won last year the International Tunneling Award with this project in the category major project over $500 billion because it's a special working site. I will explain that to you. So the project is localized at the ridge of the Alps in the west of Switzerland, at the border with France, very close to the border of Italy. It's not the first project on the region. It's the fourth project, no, because at the ridge of the Alps there is a lot of snow, a lot of water, and the Swiss Federal Railway decided in the early 1920s to build the first dam in the region. And after there is two other big dams. And now we are using this dam to build a pump storage power plant. Four Swiss companies have joined forces to build this project because it's really a major project. The budget is $2 billion US. It's exactly the same in Swiss francs, and the construction duration of the project is 11 years. It's a major one. Why are we doing such project pump storage power plant in Europe? No, because we have a problem with the electrical grid. Because we have now a lot of solar panel, a lot of such aeolian and wind machines, and there is a lot. That brings a lot of uncertainty on the grid, and there is a need of power. If there is no wind or nothing in Europe for one day, you have no power, so the electrical society have to build such new project, pump storage power plant, to be sure to have always enough power to stabilize the electricity grid. So there is some project in Europe, there was one in Austria, and there are two in construction in Switzerland. What we do with such power plant, when there is a need of electricity on the market, we turbine as usual. And for example, at night, when there is enough cheap electricity on the market, we pump. And after the following day, we turbine. Doing that, we lose electricity, but the system is a giant battery. The goal is to stabilize the grid, and the cost difference between the day and the night of the electricity price allows to amortize such project, we hope, in 80 years. Perhaps it will be shorter, it's not sure. And for that, we need two things. We need two lakes and two reservoirs with a difference of elevation between them. And to be economical, the distance between the two lakes should not to be long, and the difference in elevation should be relatively high. And we have a good example here. It's the region of Émosson. Sorry, you have here the old Émosson Lake, which is located at 2,205 meters above sea level. At the other is a giant Émosson's Lake, which is at 1930 meters over sea levels, above sea levels. You can see here. That's the first dam. That's the dam Vieux-Émosson, the upper reservoir, with an original capacity of 12 million cubic meters and a height of 45 meters. And for the project, we decide to raise this dam of 20 meters to double the capacity of the lake. The original dam was a mixed design arch dam, gravity dam. And the second lake is Émosson. It was an international project at the border of France and Switzerland. The border was originally here, and we changed the borders. You know, the French border is exactly here, but the water comes from France and from Switzerland. And so it's a really big arch dam. The height is 180 meters, and such arch dams are very sensitive to settlement and to earthquake. And the power installed actually of all the reservoir on site is 220, and that's a railway current, and 390 megawatt for normal electricity currents, 50 hertz. And now we will build a new project of 900 megawatts. It's equivalent to a nuclear power plant. Okay, that was the existing system. And now I will speak about the new project, Nanodrons. Here you can see the transport of one of the pieces of the TBM. The scheme of the hydroelectric system is very common, but there is in fact two parallel systems. And in each system there is 3 pump turbines from 150 megawatts. The same machine, turbines, and pump. And it's located in a giant underground cavern. And there is 2 other caverns for the safety valves. So here, the upper valves has butterfly valves, the lower caverns has wagon valves. And we have also 2 water intakes, two upper water intakes and 2 lower water intakes. One of the problems we had is to construct the lower water intake because the lake of Émosson was always in operation during construction. So we have to find solution to construct that. I will explain that. Another interesting challenge was the construction of the 2 shafts. And to go there it's really on the mountains. We have to access. As we construct, it was previous to have main access galleries. Originally, it was previous to do that with drill and blast, and there was a proposal of several contractors to do that with tunnel bore machine, and finally, we choose to do it with tunnel boring machine. And some contractors propose also to have 2 other access gallery, a descending access gallery also to go to the caverns, and an access gallery to the upper valves. Originally, it was previous to have a small access gallery and a cable car. And we decided to take this option because we have a lot of advantages with this option. We have, for the safety, we have 2 access to the main powerhouse, and we can go to the upper valves in winter without helicopters. Okay, here you can see the 3D model of the hydraulic system. No, first of all, the water is only on the blue, or the blue galleries. All the other galleries are cavern or access gallery, what is in gray. And no, all the galleries are excavated, and we have only 1 plug to excavate next year. And we have a small new access gallery, but it's not important. And here you can see, here you have the main cavern, the transformer cavern, the upper cavern for the valves, the lower valves caverns, and 2 small caverns for the steel linings. There is 17 kilometers of tunnel were excavated for this project. The geology, we are in the earth of the Alps in very good rocks. We have granite, orthogneiss, metagravic. This is little not so good as orthogneiss, but it was good rocks. We have only carboniferous shield at the beginning. It's an very good rocks for open TBM. So we choose this solution. We drive under the lake without problem. One of the problems we had, the rock is sometimes too good. This orthogneiss was very, very hard for the machine. The problem is related to water, I have to say. We have 2 problems. The first problem are the springs of the local community. We have to protect them. And the other problem, that's drainage of a big fault zone in this region, the risk we have is to induce settlement of the dam. We had a big accident in Switzerland in the 70s due to an exploration galleries. A dam was completely damaged and it has to be emptied very quickly, and it cost a lot of money. So we were very prudent with these problems. The machine cavern is really a giant cavern. For such type of machines, the height is relatively normal, 52 meters, the width also 32 meters. This cavern has a little sister, the transformer cavern, but this is also a big cavern. I think it's 25 meters. But what is very special with this cavern is its length. The length is 200 meters, I have to say. It's a big cavern. The volume with the cavern is 235,000 cubic meters. It's the biggest cavern now in Europe. And how it runs, we have an alternator. That's new type of alternators to optimize the pumping capacity. That's prototype. There is another of such prototype in construction in another project in Switzerland. That's a very brand new type of alternators. And the machine, that's a big machine. The flow through the machine is 60 cubic meters per second. And there is clear 2 ball valves before and after the machine, because when you want to pump, you have to empty the machine before pumping. But what we are doing there, it's really peak production of electricity. We can go from 0 to 100% of turbining in 3 minutes. Really peak electricity. No, in the electricity market in Europe, they were buying and selling a tranche of electricity every 15 minutes. They're really critical markets. And the people who have power win money. So, for the inlet tunnel, for the waterway, we try to do it without steel lining. We have to spare money. The rock is good, so we only have sprayed concrete. We do it in drill and blast. As we say in Switzerland, conventional tunneling. We never say NATM. We say conventional tunneling for our Austrian colleagues. In fact, we do exactly the same. So usual word, international for the ITA is conventional tunneling. We do that in drill and blast. We have anchors and sprayed concrete with steel fiber. And after that, we concrete with formwork a concrete lining with a very low part of steel in it. We have cracks. We have sometimes cracked in this concrete lining, but we injected around the tunnel to avoid that too much water goes in the rocks. But it's normal. It could have exchange from the tunnel to the rocks, and if the water come back when we will empty the tunnel. And we restrain the steel lining on very short portion for the bifurcation, only for that. But the risk is to have water in the cavern and water through the cracks to the cavern, so we optimize the distance of the steel lining. And so there is one constructor to install the steel lining. It's an Austrian company, Handritz, and the main contractors, the Swiss company GMI, that's Marti and Implenia, do the concreting. Here you have a project overview. The hydraulic system is really located in the mountain, over 2,000 meters. And there is no place to install a big construction site at this elevation, so we install us in the valley. The difference in elevation is more than 1,000 meters, you have to say. And we have another construction site, but at this elevation in the Alps, you cannot work in winter. And another problem we have, to go to this site, the access road is also closed in winter from November to May, due to avalanche risk. There is a lot of avalanche risk in this region. And so we drive an access rally with an existing TBM. It was the TBM of the Lötschberg. It was used 2 years in the Lötschberg. He drives 10 kilometers in the Lötschberg. After, he was used one time in Spain for 1.5 kilometers and was packed by the contractor Marty. And after, he proposes to use this TBM. And the rock is the same as that in the Lötschberg, so we accept this proposal. The roots and the length of it seems to be strange. The root and the length is given by the difference in elevation and the inclination. We fix the inclination to 12%, and it gives us the length on the roots. And what we try with this route is to be as far as possible of the dam in the region of this fault zone. And we have another piece, another road to construct. It was a descending access to the water intake in the lake. Here you can see the main construction site. Here that's the construction site. Here we have the main deposit, and here is the camp. We had last year 650 people on site. And in between, there is two electricity power plants who are in operation. It takes us one year to install the site. We had to drive a small tunnel with drill and blast to access to the site. We have to prepare the place. We have to prepare the portal. The portal is always in operation with the train. The train is between Chamonix and Martigny. It's a touristic train, but he is driving at 40 kilometers per hour at this place. And it takes us more than 6 months only to realize the portal. And that's the situation in the summer 2009. The job began in 2008, in September 2008. After that, we transport the TBM, and the TBM was mounted in 3 months, between at the end of September until December 2009. One of the problems was the accessibility. For example, to transport this part of the TBM, it takes more than 1 day, 1.5 days to transport this part on touristic roads. And that's a typical hard rock machine. The power of the machine is 4 megawatts, so we have to reinforce the electrical grid of the valley before to let the machine goes on. And the machine, the TBM itself is 20 meters long, but the machine with all the trailers is 142 meters long, and we had no place at the portal. We have only 30 meters, so we blast before constructing the machine 10 meters to be sure to construct the machine. And we first construct the TBM, push the TBM in the tunnel, and after we have constructed the trailer, and we install the trailer. And here you can see there is very good rocks. In Switzerland we have five stabilization classes, and that's very good. That's classes 2 with some Swelex balls. We had no problem. One of the problems we had is radioactivity. This granite is radioactive, so we had to manage the radioactivity. We had to control the radioactivity on the rock. We have procedure. Each meter of tunnel was controlled. And we separate uranium materials from the rest of the muck. Another problem is clearly the water. Here you see the excavation. The contractor has to fulfill it, install drainage tubes, and fulfill, create a road here. He had problem to do that. But now we have in the drainage 200 liters per second. And we don't lose this water. After we transfer this water in an electrical power system, and the water is turbined another time. It's money. It's a lot of money, I have to say. And the best advancement speed in 1 month was 700 meters per month. That's relatively good. But at the end, the orthogonal was so hard that finally the middle advancement rate of this TBM was lower than 10 meters per day. It was really not good. Huh? This machine at the Lodge Bear, for example, had to drive with 17 meters per day, and here we had more problem. Probably the inclination has not helped the machine, but also the rock was without cracks, and it was very hard for this machine, and it's quite old, it's 10 years old. The big problem we had during the excavation with the TBM was this fault zone here, exactly called Davedal. It's a free fault zone on 300 meters. And the risk we had was really the drainage of water. And if we have drainage of water, we have the risk of settlement of the dam. So the dam was placed from the beginning of the project under special supervision and management with theodolites, automatic theodolites, and such things. And we have to manage the groundwater to avoid the settlement. And normally, if we drive a tunnel without special safety, special injection measure, we will drain all the water. So we perform exploratory boring, destructive boring before the machine to control if we have water or not. And in September 2010, we find water with 42 bars. So we have to stop the water, and we decide to begin with the injection work. So, for this 300 meters, it takes us 9 months. We perform 23 probe drilling. Some of them, this one are core drilling. And what we find sometimes is zone with RMR 0. Here we have fault zone with RMR 0. Really big fault zone, more than 15, 20 meters. And so we began with injection. We perform 30 injection volts. You can see here 3 of them, 3 other, 4, and here 5, I think 5 injection valves. We drive 10 kilometers of injection drilling, and we use only 70 tons of cement. Finally, we stabilize the groundwater. At the groundwater level, we lose 100 meters of elevation, but we have only 20 to 30 liters in this zone. And the dam moves a little bit. There is a settlement of 1 centimeter, and the dam goes in direction of the fault zone from 1.5 centimeter. And there is no cracks on the dam, but there was big discussion with the Swiss dam safety authorities, and at the end, it let us fill the dam. After more than 2 years of work, the TBM arrives in the zone of the caverns. So we stop the TBM and we excavate with drill and blast a giant cavern from the TBM in order to disassemble the machine. Here you can see this cavern for the disassembly. And it takes some months to do that. And now in this cavern, we have 2 concrete batching plant and 2 parallel concrete batching plant to concrete our caverns, to concrete our tubes. And we had a lot of people working, so we decided to install a big refuge chambers on site for 200 people. It's a concrete bunker, I have to say, with the compressed air coming from outside. And the project is so big. There is so many machines, so many engines. And the heart of the system is 5 kilometers away from the portal. So the contractor decided to excavate a cavern only to have a mechanical workshop, for example. And now we are searching. There is a beautiful cavern, very good. And we are searching what we will do with this cavern at the end. One of the ideas is to install computer in it. And what I showed to you was what was done from this site, and we began 2 other access from the other construction site. We began the excavation by drill and blast in 2009, and we had to stop in November due to the winter. The problem we have is clearly the avalanche risk. Here you have the dam of Émosson, the dam of Vieux-Émosson, and the working site is exactly here. So what we do, we built a team of mountain guides to help us to manage the risk of avalanche. And this guide is supported, but we have an institute on avalanche in Switzerland. They are supported by this institute. And every time there is big snowfalls, they come with helicopter and blast the avalanches. But you see that's very, very dangerous. And we want to be very early at the end of the winter on site, so we have to open 11 kilometers of road to go on site. Take us some time. One of the questions is, where is the road? And here you can see the situation. We had a really hard winter. The situation of the working site at the end of the winter. There is one mechanical workshop of the contractor here. And that's the opening of the portal. If there are more than 10 meters of snow. And why we go so early in winter? Because we have to prepare, we have to construct our water intake. And the electricity company say to us, find a solution. We don't want to empty the lake of Émosson during one year to construct the water intake. Find another solution. So, they say to us, we give you every year a working time of windows of 2 months because the lake are empty at the end of the winter. Alors, here you can see the situation at the end of the 4th year. The first year, we come with an helicopter and we take only a machine to excavate the loose material, the soil. The second year, we blasted the portals. The third year, we blasted the 50 meters of each tunnels. And that's the situation at the beginning of the 4th year. And we have this building to construct. It is not possible to construct this building in winter. The building itself, the water intake, it's concrete building. The width is 24 meters. And the weight of the building is 1,600 tons. So what we do, we find another place to construct the building. Here the elevation is 1,812 meters above sea level, and here 917. The advantage of this site, so we have 4 months to construct the building. It's possible to access in April, and we have we have 4 months from the beginning of April to the end of July to construct the building. And after that, we fill the lake, and the lake is completely filled in September. We need only 1 meter of water, and we are ready to move this water intake. We move this water intake on 900 meters, and we immersed it with more than 100 meters. It takes only 4 days to do the jobs. We use standard immersed tunnel solution, but it completely new at such elevation. We need divers only for one operation, is to connect these cables, and for the rest, it's very, very simple. That's simple physics. We construct 2 walls here, as we create a big bubbles of air in the structure, and 80% of the weight of the structure is supported by the air. And so we can install our structure without problem. That's standard techniques. With the advantage we can install before cables to guide the descending of the structures. Here you can see the water intake before the structure, and we do only that. It seems to be very easy, and it was very easy. These structures are constructed, And one of the plug of rocks between this structure and the tunnels is already take it out because the valve was ready last year, and the next one will be ready next year. For the upper water intakes, it was a little bit easy. We emptied the lake, there is no problem, and we construct only protection dams. The excavation of the main cavern takes us 25 months. It's a big volume. For supporting the cavern, there is 14,000 rock anchors. And we have 9 steps of excavation. After the second step of excavation, we have concreting of vault. It takes us 3 months. And we go forward with the excavation. After 28 months of work, the cavern was finished. The 2 first years, we had to stop for the winter. And now we are installing the turbine. We are concreting the complete machines, the machine powerhouse. For the vertical shaft, we decided to do that with standard raise drilling techniques. The boring was very good. The precision of the boring was 20 centimeters on 400 meters, and that's absolutely perfect. That's the arrival of the pilot boring, then the installation of the cutter head. And after doing the raise drilling, we have to control the radioactivity too before to go with the enlargement. Because we were very prudent and we have uranium in this zone. And that's the vertical shaft was blasted by an Austrian subcontractors, and that's the blasting. They do a very good job. The speed of excavation was 5 meters per day. So that's good. And after that, we have concreted our shaft with a sliding platform. It was without problem, without any stops during 4 months. And after that, we have to inject around our shaft, and these shafts are ready now. Another challenge was the raising of the dam. That's our existing dams here. But as you see, that's mixed profile. It's a gravity dam. But if we want to use the same type of dams, we have a big volume of concrete to install. So we decide to change the form of the dam, the type of the dam, in order to spare money and to spare concrete. So what we do, we demolished 20 meters of the dam, and after we concreted with a new form. For the demolition, we try to do it by blasting, but it don't run very good. So we change, and we use standard road mill machines to do that in trench of 15 centimeters. No, without any problems. And after that, it takes us 2 years to concrete the dam. It was concreting in the steps from 1.5 meters. And now we have to inject between the joints. Another point that's very important in such big project is all the muck management. And as mentioned by Professor Galler, what we try to do in Europe is to use the muck to produce concrete granulate. So if you have 800,000 tons of concrete granulate to produce, so we use 20% of our material. So we have to choose the material in advance and to stock the material and produce granulate with that. There is a lot of technology in it, and we have 2 crushing plants, one for the normal concrete and one for the concrete granulate of the dams. And we have 4 muck deposits. 3 of them are final deposit. Only one is a provisory deposit, and it's very important to make it very good, because to how to say that in English, to make a big, very beautiful landscape after, because it's the only one thing we will see at the end of the project. All the system is underground. People, they will only see such things. So it's important to make a good integration of such dam, such deposit in the environment. Thank you for attention. If Mr. President let me, I will show you a film. I have time to show you a film of the 3 minutes of the project.